Hello everyone, my name is Tim Dara. I'm a PhD student at Vanderbilt University and I'm pleased to present our recent work on prognostics-based decision-making for safe and optimal UAV operations. Here's an overview of what I'm going to discuss today. However, I want to bring your attention to the figure on the right, which is of an artist's rendering of our next generation airspace that could be realizable by the end of this decade. NASA, Uber, and over a dozen other organizations are working fervently to realize this vision. However, you can imagine that in order to maintain safe and optimal operations in a congested urban airspace, a high degree of autonomy will be needed, and in this work we focus on system-level prognostics. So, what exactly is system-level prognostics? Well, system-level prognostics is tracking the entire system state of health over time and evaluating the performance of the system with respect to some operational parameters. As this system continues to evolve, we estimate the state of the system and the degradation distribution, and then make a prediction about when those performance thresholds are violated. And typically this is what is done is component level prognostics using their manufacturer's thresholds, which you can see result in much longer end-of-life distributions. System level prognostics applies this to the entire system with thresholds set by external operational constraints, and then you can find that the system remaining useful life is always much shorter than individual components. And when applied to the powertrain system of a UAV, for example, you end up with a scenario that while the battery itself certainly isn't dead and the motors might not be completely broke, their combined degradation affects the system so much that the system level safety constraints are violated, and thus the UAV is no longer safe to fly. And our experiments are only as good as the models which we are using. Here's a block diagram of the improved model from reference 14 with improved position controllers, and here you can also see the loop between the motor's battery and the control. And naturally, controlling UAV is going to become problematic as these two components degrade. So with this improved model, we can then simulate various trajectories and analyze the behavior of the UAV in flight. You can see three separate trajectories, and naturally, why would anyone think of taking trajectory C, right? Well, again, when you take a system-level prognostics approach to safety, you realize that questions such as, what is the safety risk of flight A, B, and C given wind gusts? What's the safety of flight A, B, and C given degradation? Well, these aren't easily answered anymore. You then may well say, it depends on the direction and magnitude of the wind gusts, or it depends on the degradation. Is it the battery or the motor or both? Which motor? Degradation in different motors result in different deviations from the reference trajectory. So, what actually seems like a very straightforward approach, take trajectory A, actually becomes quite complex. And the first step to being able to, fully answer these questions, or the question that we pose in the paper, is it safe to take the next flight, starts with modeling the various sources of degradation. And we model three sources. The first one is the internal resistance of the battery. And this degrades over time due to electrochemical processes in the battery. And as you can see in the x-axis, we model this in terms of discharge cycles, which is common of what we see in the literature. And the second source of degradation is the charge capacitance. Over time, the amount of charge a battery can store and be retrieved degrades due to deterioration in the electrolyte solution, or other sources. And the third source of degradation modeled is the internal resistance in the motor. This is actually a proxy degradation to simulate loss in torque or potentially increasing in the back EMF. However, for our purposes, this is sufficient. So our experiments consist of a system-level prognostics approach to UAV safety analysis with the use of a digital twin and offline simulation. And here you can see the online and offline portions working together, where online, as I said, we run the actual system. We are actually tracking the state of that system online, and then we perform degradation modeling and simulating in the digital twin offline, and then the remaining useful life calculation. So how was this implemented? Well, first we initialize everything to starting conditions, which for us, these are drawn from a distribution of healthy values. We don't hard code the actual starting value. Then the true system executes the flight, and following that, the system state of health and degradation parameter distributions are estimated. Then the degradation rate is approximated, which allows us to estimate future values. And we don't look incredibly far into the future because these degradation rates themselves are changing and they always need to be reapproximated. Then these values are passed to the digital twin, which performs the Monte Carlo simulation until the end of life. The remaining useful life of the true system is then updated, and given the amount of time into the future, the digital twin was simulated and its end of life. So with this updated information, we check to see if any safety constraints will be violated on the next mission and then make a decision, whether or not to perform maintenance or to go on that flight. Now, the mapping of these safety constraints to performance parameters should be carefully selected. And in our experiments, we monitor the UAV's trajectory and state of charge at the end of the mission. All sources of degradation impact these two system level performance parameters, so it makes sense. And here they're shown for the healthy system. And here they're shown for the digital twin. So you can see our digital twin is a suitable representation of the real system, and therefore our further results are going to make a little bit more sense now. On to the results. In our experiments, we studied the performance of the UAV both with and without the system level prognostics framework. Without it, the UAV was unable to alert the operator of true failure because it was tracking only the battery and benchtop performance metrics, which have a much longer life than both the system and operational considerations. With the framework, the UAV was always able to preemptively identify when the safety constraints would be violated, and instead of flying the next mission, would enter maintenance. So here's the results of a flight under nominal conditions, where the UAV starts in the bottom left. It must fly to the middle right to deliver a package and then fly back to the arrival point. And here is the result of a flight under degraded conditions in which the performance parameters were violated. First, looking near the delivery point, you can see that the craft was not flying at the desired speed because the path near the delivery point was generated with a time vector to change the color of the delivery and return paths. And you can see here that it was about 30 meters away at the time it was supposed to have reached delivery. Then in the middle of the path back, it crashed. And so what do our performance parameters tell us about this? Well, under nominal conditions here, you can see there's about a 1.5 meter deviation. We end up with about 47% state of charge and a 4% battery voltage remaining. The degraded flight tells a much different story, and pay attention to the current plot as this changes. So you can see we have a lot more sustained variation in current on the degraded flight than we did in the previous flight. And we also have this unbounded deviation and tracking error that ultimately results in the system level performance constraint being violated and the flight is stopped. And so before the UAV ever gets to the point of violating a performance parameter, we employ our framework. And here the prognostics algorithm tells us that, hey, it's time to perform maintenance, and for our purposes, we do not care exactly what that is. We just show that if we address the sources of degradation, which ultimately rewinds the clock on the degradation parameter values, then the UAV can safely continue to fly. And here, those values were reset according to a distribution of values in the healthy range, and the flight performs nominally. So what is the key takeaway from this research? Well, component level prognostics will no longer suffice with the level of safety our ever advancing technology requires, and it will always lead to a false sense of health and operation beyond the system's true limits. With this approach, we get a better understanding of the true remaining useful life of the system, which then allow us to make better informed operational decisions down the line. In this study, one of those operational decisions was whether or not to fly the next mission or to take maintenance. Here we can see that without this approach, the system will ultimately violate their performance constraints, which lead to failure, after which the UAV can no longer fly any missions. With this framework, preemptive decisions are made regarding the system's ability to fly within the bounds of the safety constraints, and maintenance actions are taken before failure. The UAV is able to continue to fly beyond the original failure point of 103 hours and always remain within safety bounds. So there's a lot of future work that can be done to build off these results, and one of them is going further into the maintenance activities, which in our work we simulated, but we know that there's a lot more detail that is involved that could be explored. Another area of exploration is looking at fleet-wide mission and maintenance scheduling. What does it look like when we have several UAVs and multiple missions and limited number of maintenance spots? This becomes a very interesting scheduling problem. And then finally, what about the integration of cloud computing? What types of computing can we deploy to the cloud, and what can we do on board? And how will this further enable the transition into commercial technology? These are all areas of future exploration that I hope will be addressed in the coming future. And again, my name is Timothy Dara. I hope everyone found this presentation informative and insightful, and I will now address any questions that anyone may have.